Hitting record again. Okay, so reading responses generally fairly positive, and people seemed surprised that they were positive. Meaning, I got a whole lot of people saying, "Oh, wow, when I first started reading this section, I thought this was going to be really hard, but it really feels just like you're doing all the derivative stuff backwards." Yes, that is exactly what you're doing when you do an antiderivative, is you're just undoing all of those derivative rules that we learned before. Now, we didn't undo all of them in this first reading. We undid the big ones, like, what did it look like to do the power rule in reverse? What would it look like to anti-differentiate a constant rather than differentiate a constant? And so on and so forth. But again, most people seemed fairly comfortable with most of the section, with a couple of exceptions. One, a whole lot of folks said, "Oh, that example 5 with the trig functions, I was a little confused by that. Yeah, I should not have asked you to read that. I was thinking, I told them to not read example 5. And then I went back and looked at my notes, and I had forgotten to include that in the reading instructions. Oops, my bad. So again, there's not going to be any trig functions on problem sets, quizzes, tests, exams. We've done no trig functions throughout the entire semester, and we're not going to introduce them now. Okay, so again, that was just an oversight on my part in terms of the reading. There was also an example that had you do integrations of functions that looked like this. That was in the second half of example 4, and it gave a shortcut for that anti-differentiation. Yeah, and there's actually going to be a better way to shortcut this in 1 week from today. So we're not going to do any problems today that are of this format either. Now, you will see problems of this format in under a week. So don't think that the trig functions you'll never see with this course, but functions of this type you will. We're just not going to deal with them today. Okay. All right. Now let me do a share to my whiteboard on my table so we can get a quick summary of the things that we know. There we go. Finally. Okay, so first note that an antiderivative and an indefinite integral are the same thing structurally, meaning you're doing the same operations. You do, however, use slightly different notation to do it. So, for example, if we wanted to use an antiderivative notation, you would say something like this. If f of x is equal to some constant, we'll call that k, then the antiderivative, which would be uppercase f, would be that constant times the variable of integration plus some arbitrary constant. What we're getting out of this is an antiderivative family of functions. So as an example, if f of x is equal to 3, then its antiderivative is 3x plus any arbitrary constant that you like. And the reason why is if you took the derivative of 3x plus an arbitrary constant, you would get 3. So you can always check to make sure that you've done your anti-differentiation correctly by taking the derivative of big F and seeing if it gets you back to little f. Now, this shortcut right here for antiderivatives could also be written as follows. It's an indefinite integral. And it would read like this. Obviously, this is a lot more compact, and so we're not using any of the if-then language, but it can also be really easy to kind of lose track of what means what. So this is the biggest mistake that I see people make. These two symbols, what we'll call an integral symbol, or we could call it a soft summation, a soft S, a squiggle, anything that you like. But this S notation over here and the DX right there are paired together. It's kind of like opening and closing parentheses. They have to both be there in order for it to do what it's going to do. So we would call this the integral operator. It is an operator. It has to have something to operate on, and the thing that it is operating on is the function k, and that function k is referred to as the integrand. Now, what most people will end up doing is just playing real fast and loose on that dx. They'll have the squiggle part, but not the dx. But remember, it's the two of those together that create the integral operator. I will also frequently use the term integrand and say, oh, you need to simplify your integrand, and you need to know what it is that I'm referring to. It is the function sandwiched between the squiggle and the dx in your integral operator on which you are performing your antiderivative operation. So this is what we're ending up with as our result is our antiderivative. And it is the antiderivative of the integrand. Now, you'll find that I end up using the indefinite integral notation a lot. Again, it's very compact, and what can I say? Mathematicians tend to be lazy in the way that we write, but that's actually not true. We tend to be compact in the way that we write. Why use more symbols than you have to? All right, there we go. Okay, so again, we would interpret this shortcut right here, which is how you would anti-differentiate a constant, in the exact same way that we would interpret this shortcut here using the indefinite integral operator. The result that comes out is still going to be the same. Now, let's take a couple of more of those. I would like to erase this, if I may. Okay. Let's take another antiderivative shortcut. Now, this would be our antiderivative shortcut for the power rule, how we undo functions that are being expressed in terms of a power. Now, we'll get to in a minute why this particular ordering makes sense, but a most important thing to talk about here is that we can't use this rule if n is equal to -1, because if n was equal to -1, we'd have a 0 in the denominator, and that's really bad. The exact same shortcut as an indefinite integral would read like this. So there's my squiggle and my dx surrounding the integrand of x to the n, and the result of performing that indefinite integral operation is the antiderivative right there. And again, we'll make our little note here that n cannot equal -1, because then this would be undefined. All right, now let's talk about why it makes sense. So say that f of x is equal to x cubed. This shortcut would say, all right, I'm going to raise my power by 1, and then I'm going to divide by whatever that new power is. And don't forget your arbitrary constant of c. Now, you can always check to make sure that you've done an antiderivative correct by taking the derivative of the antiderivative and seeing if it gets you back to where you started. How would you describe the shortcut for taking derivatives in words? Again, feel free to do it loosely. Anyone want to give it a shot? The shortcut for derivatives in words. Who wants to give it a try?
Are you talking about in general or just specifically for the power rule?
For the power rule.
Oh, okay. I can try.
Okay, go for it.
So you would put the so if you have x to the n as your base function, you would
Yeah.
put n in front of your x, so multiply the exponent times your x. And then, you would raise it to the power of n minus 1.
Okay. Now, if we were to apply that here, that 1/4 is just a constant multiple. It just keeps track of how many of what's going on. Based off what you described there, Sarah, which was correct, you bring your power down to the front and then you reduce your power by 1. The derivative of an arbitrary constant is 0. 1/4 times 4 gives you just 1. This whole thing is going to simplify to just be x cubed, which is the thing that we started with in the first place. Oh, that's a way in which you can use derivatives to show why the antiderivative rule works. But here's another way that's actually really important for how to keep it straight. What Sarah described doing was actually a really important order of operations. You take whatever that power is, and when you differentiate, first you're going to multiply by that power, and then you're going to subtract 1 from that power to generate a new power. So multiply, then subtract. Great. If you are undoing, if you're going backwards, then you have to do the opposite of each one of those operations and in reverse order. It's kind of like, driving from your apartment to a friend's apartment for the first time. If you drove north for 1 mile, then to get home, you're going to have to drive south for 1 mile. If you took a right turn to get into their parking lot, you're going to have to take a left turn to get back out again. So every operation was undone by another operation and in reverse order. Drive 1 mile north, take a right. To get backwards, you would have to take a left and then drive 1 mile south. Okay, so derivatives say in this order: multiply, then subtract. So if you want to undo that process, then when you're doing an antiderivative, you have to undo the subtraction first by adding. That's right here. And you have to undo the multiplication by dividing. That's right here. So you're going to be adding 1 to your power first and then dividing, not the other way around. Now, again, you can always check that by taking the derivative and making sure that everything worked okay. Now, that same example being applied right here. Would read as follows. Again, a lot more compact way to say what we're saying up here. The plus C is critical because what we're getting out of this is not a single answer, but an infinitely large family of answers from which we could pick any arbitrary constant that we like. All right, so I've already written down the shortcut for a constant and the shortcut for powers, as long as your power is not -1. Let's get a couple of more out there. So this would be the case where your power of x is actually -1. because we could rewrite that as x to the -1. Now, we can't apply the power rule here because we'd end up dividing by 0, and that is clearly evil. So really, instead, we have to think about it in terms of what function, if we took its derivative, would give this as the result. And we get the natural log of the absolute value of x. Okay, that's actually really important. What is the domain of the natural logarithmic function? If anybody knows that, I would love to hear it. What are the values that can go into a natural logarithmic function?
Anything but 0?
Well, 0 is definitely bad, but you also actually can't take the natural log of negative values either. If you were to pull out your calculator and ask it for the natural log of -2, it would tell you it can't compute. Now, the 0 is also a problem in this function right here. So the fact that I can't have a 0 here and I can't take the natural log of 0, both those functions share the same problem. So that's okay. But a -2 right there wouldn't be a problem, but a -2 over here would be. That's why you have to have that absolute value, is to guarantee that you're not going to be taking the natural logarithm of anything that's negative. So keep an eye out for that. That's another one of those little things that what people will often overlook. It's really just to make sure that we don't throw anything into the natural logarithmic function that's going to cause it to break. Now, as an indefinite integral, this would read as follows. Now, really the only last one that we have to deal with then is e to the x. Say e to the x is the only function that it's its own derivative, so it's also going to be the only function that is its own antiderivative. And again, we know this is correct because if we took the derivative of e to the x plus any number, the derivative of e to the x would be e to the x. The derivative of that constant would be 0. It would end up taking us right back to where we started. And then its indefinite integral version looks like this. Ta-da. All right, so for today, we've got 4 major forms that you're having to keep your eye on. How do you anti-differentiate a constant? How do you anti-differentiate a power? How do you anti-differentiate a 1 over x? That's going to get us to our logarithm version. And how do you anti-differentiate e to the x? That's really all we're going to be doing today, is practicing those. There's still lots of possible things that can go wrong that are mostly due to notation. So let me give you a couple of examples to show you what I mean. Okay. Yeah, I'm going to erase this. Let's take something like this. It doesn't look like we have a rule to be able to address the square root of x, but recall that the square root of x is just x to the 1/2 power. And the +1 is staying the same. This is similar to before when we were doing derivatives, where I said, hey, don't differentiate any part of your combination until you can differentiate everything. That's exactly what's happening here. We could anti-differentiate the 1. We'd be ready to roll with that, but we're not ready to anti-differentiate the square root of x until we write it as x to a power. At this point, we're ready to apply our antiderivative shortcuts. Now, our antiderivative shortcut for this power, x to the 1/2 power. The first thing you're going to do is add 1 to the power. Add 1, not subtract 1. So you'll end up with a 3/2, and then you're going to have 1 over that new power over here. That's probably making some of you a little uncomfortable to see a 1 over a fraction. It's actually all right. You can leave it just like that. That'd be fine. Now, the antiderivative of 1, remember that's our constant, and the antiderivative of a constant is just that constant times x. So we would have just plus x, and then our arbitrary constant within the family of c. Now, you could stop right here, just walk away, and that would be perfectly all right. You may, however, not be able to avoid the temptation of re-expressing 1 over 3/2 as 2/3. Dividing by a fraction is the same thing as multiplying by its reciprocal. So we just did an invert and multiply there. And the reason why is because the check is a little bit easier to do if we have it in this format. So I'm going to differentiate my big F, and I get 2/3 times 3/2 x to the 1/2, because I multiplied and then subtracted 1 from the power. The derivative of x is 1, and the derivative of that arbitrary constant is 0. Those cancel. I have x to the 1/2 plus 1, which is the same thing as the square root of x plus 1, which is right back where we started. Again, I anti-differentiated, and then I differentiated to see if it would take me back home again, and it did. Again, the biggest errors that people will make here is not being clear what the original function is versus what the antiderivative is. We've come across this before, and so you'll want to have some extra attention to that detail. Now, let me just show you really briefly what this would look like if you were doing it with the indefinite integral operator. I'm going to erase some of the work here. If you wanted to do the exact same problem using the indefinite integral operator, like this. Again, we got our squiggle and our dx surrounding the integrand. The integrand, however, is not ready to roll. So we leave the operator present and just make an algebraic manipulation on the integrand. And now it's in a form that our antiderivative shortcuts can handle. I will anti-differentiate x to the 1/2. And I got 1 over 3/2 x to the 3/2. I'll anti-differentiate 1. That gives me x. Don't forget your arbitrary constant of c. Again, making sure that you're holding on to the squiggle and the dx until you actually do your antiderivative. Another example, I would like to erase this. Okay. Let's take something like this. We'll do this one as an indefinite integral. Now, this piece right here is definitely not ready to do a power rule for anti-differentiation. Here's the interesting part, though, is that you might look at this one and go, oh, I need to rewrite that as x to the -1, and this one as x to the -2, and this as 6 to the 1/2. Now, that statement is 100% correct. It also is not 100% helpful. It was helpful for this term because I needed to have x to a power in order to be able to apply that power rule. But it's not helpful here because, yeah, I wrote it as a -1 power, but my power rule can't handle a -1 power. So this as a rewrite didn't really get me anything. So I'm going to leave that alone. Now, this also not wrong, but also perhaps a little bit misleading. Yeah, the square root of 6 is the same as 6 to the 1/2, but this is not x to a power. This is just a number, the square root of 6. So this is a constant, not a power function. And so writing it as if it's a power function might lead you to an incorrect assumption. So I'm going to go ahead and leave that one as the square root of 6 as well. Now, again, not immediately obvious that this was the only one that needed changing. But now we've got 3 different functions that follow 3 different rules. This one was our natural log antiderivative, the natural log of the absolute value of x, so that we don't take the natural log of anything negative. Here, I'm going to add 1 to my power, so that'll be x to the -1. And then divide by that new power, 1 over that new power of -1. So that's applying the power rule there. And this is just a constant, and the antiderivative of a constant is that constant times x. Don't forget that you could have any constant stuck out there on the end, and when you go through the check it with the derivative stage, the derivative of that constant would be 0. Again, you could type it in just like this into WebAssign and it would be accepted as correct. You could do this in a written submission or on a test and I would accept it as correct, but you also might just not be able to avoid the temptation of going, oh, 1 over -1 is -1. So that's negative x to the -1 plus the square root of 6x plus c. But again, either one of these is correct. Now, the last note I want to make is about the plus C. Okay. This got pointed out in Alyssa's reading response. She said, oh, the result of doing an indefinite integral, like what we're seeing here, is a function, and the result of doing a definite integral is a number. Yes, so important to make that distinction. These symbols look almost identical, so it's really easy to conflate them and think that they're talking about the same thing. No, an indefinite integral is giving you functions, and a definite integral is giving you just a number. Here's the one adjustment that I'd make to that, though, is that an indefinite integral is giving you an infinite family of functions. That plus c could be anything that you like. Let's say I could do a +1, a +7, -342. Any one of them would still satisfy the antiderivative property. In other words, antiderivatives are not unique. When you take an antiderivative of a function, there is an infinite number of possible answers. And that's what that plus c represents, is the infinite number of possibilities. Now, does that mean that you can never figure out what the c is? No, heck no. Let me erase this. Now, say I've got the function f of x is equal to x squared plus e to the x, and I want to take its antiderivative. Hold on just one second. I'm trying to get a sketch of something. I need to have this. Sorry that I didn't have this ready. There we go. So the antiderivative family, big F of x, we're going to apply our antiderivative properties for the power function. So I'll raise my power by 1 and then have 1 over that new power. The antiderivative of e to the x is just e to the x and then plus c. Now, roughly sketched, very roughly sketched, what it would look like to have these infinite number of families is to have a whole bunch of functions that are all parallel to each other. They're never going to touch each other, and which one of these you would pick depends on what the plus c is. So if you ever want to find the plus c, you have to be given another piece of information, something like this. So if you were also given something like that, that f of 0 equals 2, then graphically you would say, all right, then I need to figure out which one of these passes through the point 0, 2. All right, now the way we're going to deal with that is that we're going to plug a 0 into this arbitrary family function. That's going to give us 1/3 times 0 cubed plus e to the 0 plus c. And this relationship says if you plug 0 into the antiderivative function, you'll get a 2 out. All right, this term is 0. What's e to the 0?
It's 1, right?
Anything to the, yeah, exactly. Anything to the 0 power is 1. So 1 plus c is equal to 2, and therefore c must be equal to 1. That tells us that if we want to pass through this point, then 1/3 x cubed plus e to the x plus 1 passes through the point 0, 2. That seems likely to be this one right here. So there is one and only one point function, one of these versions that passes through that point. So you can eliminate all of the other options. Now, we know that there is only one choice there because we need to have a function that if we plugged in a 0, we would get out a 2. If there was some other variation of this that also plugged in a 0 and got out a 2, it wouldn't meet the definition of a function because we wouldn't have that relationship from input leading to output. Remember, all the functions were parallel to each other. They were not touching each other, and therefore there can only be one that passes through the provided point. Okay. I think the best thing to do at this point is just let you get into the list and start cranking through these suckers. Because again, you get these rules down by going through the rhythm. Most of the examples that you're going to see in the problem list are going to be ones where you're applying that power rule. We use that a ton when we're doing derivatives. We also use it a ton when we're doing antiderivatives, but keep an eye out for things that can be a little bit tricky, like the 1 over x. Looks like you could use a power rule, but you actually can't. That's going to be our natural log application. Now, when you look at the list, the problem list, you should see that some of them are just a direct application of the antiderivative shortcuts, and then there's ones at the bottom that require you to do a little bit of algebraic manipulation to the function or the integrand first. So you at least have some idea of which ones require that extra step of work. Okay, let's get you into your breakout rooms and you'll be ready to go.